Hello everyone. Have you ever wondered what really happens when you clap your hands, pluck a guitar string, or even shout across the room? Why do your ears suddenly come alive with sound? Well, welcome to the magical world of vibrations. Yes, that invisible little dance every object performs before we ever hear a single note. Sound, my friends, is nothing but energy on the move, an energy that travels from a vibrating source straight into your ears. Imagine a ruler fixed at one end of your desk, flick it, and it starts to move back and forth rapidly. That motion, called vibration, is what produces sound. So, whether it's your vocal cords buzzing while talking or a guitar string humming after being plucked, it's always vibration doing the work. And here's the golden rule: no vibration, no sound. Silent objects don't produce sound, they're just standing still, minding their own business. But give them a nudge, and voila! You've turned mechanical energy into music. Now, let's get experimental, because physics isn't real until you hear it and feel it. Take a tuning fork, strike it gently on a rubber pad, and there it is. That faint humming tone is sound in action. Bring it close to your ear, you can hear it vibrate. Now, touch one of its prongs carefully. Did you notice? The sound stops instantly. That's because you've stopped the vibrations. No vibration, no sound. Suspend the tiny table tennis ball on a thread and touch it with the vibrating fork. Watch how the ball jumps back. The fork actually pushed the air and the ball away through its mechanical vibration. See how fascinating that is? The tuning fork proves that sound is caused by mechanical vibrations, nothing magical, just physics shaking the world, literally. Alright, let's talk energy, because in physics, nothing really happens without it. Remember the law of conservation of energy? It says energy can neither be created nor destroyed, it just changes form. When you clap, you're using mechanical energy from your muscles to push air molecules around. That mechanical energy transforms into vibrational energy, and soon, your ears receive it as sound energy. Think of it as a little energy relay race, mechanical vibrational sound. Or E sound equals E vibration equals function of E mechanical. So next time someone claps, sings, or drops a spoon, remember, you're literally hearing energy being transferred from one form to another. That's what makes the universe noisy and exciting. Now, let's dip our experiment, quite literally, into water. Take your trusty tuning fork again. Strike it gently and touch one of the prongs to the surface of water. What do you see? Ripples. The water moves in little circles, not because of magic, but because vibration energy is passing from the fork to the water. Now, dip both prongs into the water, splashes everywhere. That's high amplitude vibration transferring more energy into the liquid. This experiment shows that vibration doesn't just happen in air, it can travel through solids, liquids, or gases. Wherever particles can bump into each other, sound can pass through. So, if someone tells you sound can't travel in water, just remember, even fish have conversations down there. Okay, let's make some music now, physics style. Every instrument you've ever heard, from a flute to a drum, works because something in it vibrates. In a guitar, it's the strings. In a tabla or drum, it's the membrane, that stretch surface you hit. In a flute or trumpet, it's the air column inside that vibrates beautifully. The faster the vibration, the higher the pitch, like a mosquito buzzing near your ear, annoying but educational. The slower the vibration, the deeper the tone, like a thunder drum. So, the material and shape of each instrument decide how it vibrates. That's why your flute doesn't sound like your guitar, even if you play the same note. Alright, time to get a little mathematical, but don't worry, we'll keep it light. Suppose you have a tuning fork that completes 660 vibrations in 2 seconds. We want to find its frequency and time period. Frequency, denoted by F, equals number of vibrations divided by time. So, F equals 660 divided by 2, which gives 330 Hz. That means it vibrates 330 times every second. Now, the time period, capital T, equals 1 divided by frequency, that's 1 divided by 330, which equals 0.00303 seconds. So, the fork's time period is about 3 thousandths of a second, incredibly fast. And since this frequency is within the human hearing range, 20 to 20,000 Hz, it's clearly audible. So yes, what you're hearing is pure, measurable physics. So, to sum it all up, every sound you hear, from a whisper to a thunderclap, starts with vibration. These vibrations convert mechanical energy into sound energy, which then travels through a medium like air or water. The particles of the medium don't actually travel, they just jiggle back and forth, passing the message like a game of pass the parcel. Depending on how fast and how strong these vibrations are, the sound you hear can be soft, loud, high, or low. From musical instruments to animal calls to even your own voice, it's all just physics in motion. So next time you hear your phone ring or a bell chime, think about this: somewhere, something is vibrating just for you to hear it. And that's the beautiful rhythm of physics. I hope you enjoyed exploring how vibrations bring our world to life with sound. See you in the next session, where we'll make the air itself dance again, in the science of sound propagation.